Lesson 2-8, the derivative as a function. Objective. Can you find the derivative of a function at any point x? What is the relationship between the graphs of f and f prime? What is the relationship between continuity and differentiability? In the preceding section, we took a look at f prime of a, where a represented any point on the domain of the function. So instead of using a, let's go ahead and use x, the variable x. X stands for any point on the domain as well. We call it the derivative of f. It has these nice, this prime symbol right here, f prime of x here. And f prime is called the derivative of f because it has been derived. We've used this limiting the secant line to come up with some kind of rule or formula that will give us this instantaneous rate of change. Okay, let's go through tracing a derivative, and this is our GeoGebra again. And here we have the function. Right over here is a tangent line, and the tangent line looks like it has a slope of 7, and 7 is graphed right here. Now it's telling us to go ahead and drag point A. So when we drag A, it's going to find another slope, and then it's going to graph it. And we're going to drag it more, and it's going to graph 5.57 at this point. And as we go, what it's doing right here in the green is it's graphing the slope each time. So each time I move it, it sees the slope and then it graphs it. Now you can see we're getting to this top, and we're going to get a horizontal line. And you can see right here, it's kind of past the origin, and because now the slope is negative. And as you see me tracing here, you can see that this slope is negative, and it's graphed the slope of a negative slope. And then we get to this turning place, and we're going to get to a horizontal slope, and you can see it's back graphing on the x-axis. And then we're going to have slopes that are positive, they're increasing. You can see the little triangle there showing the slope, and we have that over here. Let me trace back for where we just came from, and there's a 0, and let's keep going, and you can see the slopes are more and more negative right here. So this is tracing the derivative of a function. Now this green part represents the slopes at every one of these x values that I went through, and you can look back and you can see, hey, this looks like a parabola. So here was a cubic, and here is a parabola right here. And you can have fun with this. You can change the f of x and try other things and do your tracing as well. Okay, let's take a look at doing some sketching the graph of a derivative as well. Here is a graph. You don't know what the function is, and what we would like to do is see if we can't graph it. So we're going to play tracing as well. What you want to do is you want to look for key points like this point right here. This has a slope of 0, so right down here I know one of my graphs for my f prime right here, I'm going to do it in red, will be 0 here. And right here there will be a 0 tangent, so right here. Now from here to here were all slopes that were positive, and this is probably, at this point, was the most, the steepest slope. So I'm just going to go like this and then go down. And from right here, looks like there's another 0 slope, so I'm going to put it right here. And then all the time from this 0 to this 0, these were negative values, and this was probably the steepest it was here. So I'll just go down like this. And you can see from here on, we're going to have positive tangents that are increasing and in their steepness. And then over here, these are negative slopes, getting more and more negative as you go toward negative infinity. So it looks something like that. Let's take a look at the next curve. They did much the same thing that I was doing. Now, they may have gone up a little higher or a little lower. We really can't tell here. And when I see this, that when you do it, the key points will be here. Do you know where the zeros are? And how far up or how far low isn't important to me. It's just that you know that you have to go up and down, and then down and up, and then you go on like this. So the the extent at which you make these aren't as important as the character of the curve that you do. Okay, we want to find a formula for this derivative, and so we're going to go back to the steps we've done before. We're going to try to find the derivative. Instead of a, we're using x, but we're going to go through the same process. The limit as h approaches 0 of f of x plus h. All we're doing is using x instead of the a that we did before, all over h. Okay, and sometimes we will just work with this portion right here, get it simple, and then take the limit. So that's what I think I'm going to do here. I'm just going to find this part right here. So I'm going to put the x plus h into the formula. So this will be x plus h to the third power minus x plus h. So I've done this portion right here, minus, and I'm doing f of x, so this will be, I'm going to put a parentheses here because I want to subtract that whole f of x, and that'll be x cubed minus x, and over here, and then I'm going to divide it by h. Now you see, I'm just trying to find this portion right here. Now I'm going to expand it, and when I expand it, I'm going to have x cubed plus 3x squared h plus 3x h squared plus h cubed. I'm going to distribute the minus sign, minus x minus h, and then I'm going to distribute minus x cubed plus x all over h. And I'm going to get some things to go to 0, and this one and this one go to 0. Okay, and let's see, I can now divide, and when I divide each term by h, I am going to get 3x squared plus 3xh plus h squared minus 1. And so all of this has been just this work. Now I'm going to find the derivative, but to find the derivative I actually have to take the limit of this expression of this difference quotient that I have simplified. And I know as h goes to 0, this will go to 0, this will go to 0, and I'm going to be left with, these are the terms that don't have any h in them, so this will be 3x squared minus 1. And so this is my derivative or my derived function. And so this is a cubic, and you can see my derived function is a quadratic. And here's what the graphs look like. Here's the cubic, and here's the quadratic. And you can see that that kind of makes sense because here's the slopes of my tangent lines. They are right here and here. And before that, I had positive slopes, which is this. Here I have negative slopes, which is this. And I have positive slopes after, which is this. Okay, let's see about finding the derivative with root x. And we're going to go through our definition as well. We're going to put this x plus h into the square root formula, x into the square root all over h. Now this is the difference quotient, but you can see I have square roots. If I were to substitute h right now, I would get a 0 over 0 situation, which is an indeterminate form. So we have to use one of our techniques for our limits, and this is multiplying by the conjugate. And when I multiply by the conjugate, I'm going to multiply these two, and I'm going to get that. The outer and the inner term are going to cancel, and then I'm going to multiply these, and I'm going to get that. And at the bottom, I will get this. Don't worry about distributing it all. What's nice is that right here, this is going to go to 0, and I'm going to have an h here and an h here, and I can do some reducing, and I'll get this. Now if I let h go to 0 and replace the h with 0, I will get this expression and this expression. And so here's my derivative or my derived function. And notice that because of, I had a domain issue here, and the domain issue was that x had to be greater or equal to 0. And in here, the domain issue is even more strict. I'm going to have to say the domain is x is greater than 0 because this expression's in the denominator, and I'm not allowed to have 0 as one of the domain points. Okay, so here's the relationship between y equals root x and y prime equals 1 over 2 root x. And you can see that it makes sense. All of these slopes are positive, and they seem to be, the slopes are less and less steep. So at first they were very steep, and they became less and less steep. So it makes sense.